this video, we are going to look at yet another application of derivatives, meaning a real-life problem which you have to translate first into the language of mathematics and then use your knowledge on derivatives in order to get the right solution. In this case, we have a sheet of metal, which we will divide into 3 equal parts, of which the width we will call small l. Now we do so because we can fold this sheet of metal along these lines into this 3-dimensional structure, for which each side has of course the same length L. Now the only variable that we have is this angle right here, the angle alpha, which defines the slope of our structure. Being a 3-dimensional structure, it can of course hold a volume. For instance, you could use it as a gutter on your house. In this case, you want it to transport as much water as possible, and this translates into the volume needing to be as large as possible. And of course, you probably already see the question coming. For which alpha, so for which angle, will this volume be maximal? And this will be the extremum problem that we're going to solve. Now at this point, the problem is still in 3 dimensions, because we need to find the maximal volume. And this can be quite tricky. However, we can realize that if we take a cross-section, for example, this one right here, of our volume, then we reduce the problem to 2 dimensions, because we can realize that the largest volume will correspond to the shape which has the largest area of its cross-section. Thus, we have reduced the problem from finding the largest volume to finding the largest area of the cross-section, and this cross-section is a trapezoid. Thus, given that these sides are all equal to small l, we need to find this alpha, which is equal to this angle, such that the area of this trapezoid is maximal. This means, of course, that we first need to write the area of this trapezoid as a function of alpha. So we need to find a function a of alpha. Having found this function, we need to derive it to our only variable alpha, and then set this derivative to 0. And if we solve this equation, we will find the right alpha. However, as is the case for most of these derivative applications, taking this derivative and solving this equation for alpha is not the most difficult part. Instead, it's finding exactly this function that we want to optimize as a function of our variable. In this case, we need to find the area of a trapezoid as a function of this alpha. And that's exactly what we will do in the next step. Of course, you can very easily find the formula for the surface area of a trapezoid. Let's say that you have a trapezoid with the long side being B, the short side being A, and the height of the trapezoid being H. Then we can find that the area of this trapezoid is simply B plus A divided by 2 multiplied by this H. Thus the problem boils down to finding these 3 variables. However, for our problem, we were only given the length of these sides right here and nothing else, except of course for this angle alpha, which is the unknown and the variable which we're trying to find. To make some progress, we first define the height of the trapezoid. This will be a line which has a right angle right here, and we will call it h. The same can be done on the other side of the trapezoid with here a right angle, and we'll call this h. Now, because these are 2 right angles, we know that this piece right here, this length, will simply be L, the same as this L right here. And the remaining parts of our trapezoid on both sides of this L, we will call B prime. Thus we see that this B right here is simply B prime plus L plus B prime. And the h that we're looking for is simply h. So at this point, let's write down the surface area and then later worry how we will get this alpha inside of this formula. So first we have B, which will be L plus B prime plus B prime. Now we add to this A, which in our case is L. So A is L. We divide this by 2, as the formula says, and we multiply this by h. And we can simply write down h. Of course, we didn't really do anything yet, because we don't know h and we don't know b prime. And additionally, we still don't have this alpha in our formula, which we are desperately looking. We're looking for a as a function of alpha. And to find b prime and h, we're going to use some trigonometry, and in specific, looking at this triangle right here, or equivalently, this triangle right here. First, let's look at h. We see that h is equal to this side right here, so L, multiplied by this small angle here. But we know, since that this angle is 90 degrees, that this angle, this small angle, is equal to alpha minus 90 degrees. Therefore, h will be equal to L multiplied by the cosine of alpha minus pi over 2, 90 degrees. And this is a large step forward, because we see that we've rewritten h, which we don't know, as a function of L, which is a given, and our alpha here has entered the formula for our surface area. And something very similar can be done for b prime. We see that this will be equal to, again, this length, so small l multiplied now by the sine of this small angle, because we're looking at this side right here. And again, this small angle is equal to alpha minus 90 degrees. So we can multiply L with the sine of alpha minus pi over 2. And thus we've rewritten these b primes as a function of L, which is given, and our alpha that we're looking for. And now these two equations can of course be used to substitute into our formula for the surface area right here. And this will give us the following. We have 2 times L, taking this L and this L together, plus 2 times b prime, but we know that b prime is simply L multiplied by the sine of alpha minus pi over 2. So we have 2 times L multiplied by the sine of alpha minus pi over 2. We divide this by 2. And then of course we still multiply it by h. But h, as we know, can be rewritten as L multiplied by the cosine of alpha minus pi over 2. So this will be L multiplied by the cosine of alpha minus pi over 2. And before we go on with our calculation, let's first simplify it a bit, specifically by looking at this sine and this cosine. Now we know that the sine or the cosine of an angle minus pi over 2, so an angle minus 90 degrees, can be rewritten by the other function. The sine becomes a minus cosine, and the cosine becomes the sine. So let's first do this. Then we get, again, our 2 times L, which doesn't change, 2 times L multiplied by minus the cosine of this angle, so minus the cosine of alpha. And again, this is just this term rewritten using goniometric functions. We divide this again by 2, multiply by L, and this cosine of alpha minus pi over 2 becomes the sine of alpha. So we multiply by the sine of alpha. We see that this 2 can be dropped because it occurs in each term, and we get the following. We get L minus L times the cosine of alpha, and then this we multiply again by L times the sine of alpha. And if we factor out this L right here, then we get L squared multiplied by the sine of alpha times 1 minus the cosine of alpha. And again, this is the area of our trapezoid as a function of alpha. And we see that we did our job well, because we indeed have the area of our trapezoid as a function of things that we know. L is a given, and we see this alpha occurring right here. So the most difficult step is already over. What we now need to do is take this function, calculate its derivative to the variable alpha, and then put it equal to 0. And then solving this equation will give us the solution, the right alpha. So let's go to step 3 and finish this exercise. Just as a reference and to make it easier, let's first write down our function. We found that a of alpha is equal to L squared multiplied by the sine of alpha, which is multiplied by 1 minus the cosine of alpha. Now, of course, we need to derive this function. So we need to find dA over d alpha, which is of course the derivative of a product, because we have here an alpha and we multiply it with an alpha right here. But of course the product rule is not that hard. The L squared can be brought outside of the derivative because it's just a constant. Then we first derive this one and leave the other one untouched. The derivative of the sine is the cosine of x. So we have the cosine of alpha multiplied by the thing that we leave untouched, 1 minus the cosine of alpha. And then we add to it, now leaving this one untouched and deriving this one to alpha. Thus we get the sine of alpha multiplied by the derivative of 1 minus the cosine, which is the derivative of minus the cosine. And since the derivative of the cosine is minus the sine, we get two minus signs, and we simply get the sine of alpha. And we close our brackets. Rewriting this even further, we get that this is equal to L squared multiplied by the cosine of alpha minus the cosine squared of alpha plus the sine squared of alpha. And now this is the equation which we have to put equal to 0. So we need to find a specific alpha for which this equation is equal to 0. Thus, ideally, we would want to rewrite these three terms here as a product of terms to factorize them, because a product is much easier to put equal to 0 than its three terms. Now, using some trigonometric identities with the double angle and so on, which I will leave as an exercise for you, or I will make a future video on it, we get that L squared multiplied by 2 times sine squared of alpha divided by 2 multiplied, and this is where the factorization comes in, 2 times the cosine of alpha plus 1. And this again has to be equal to 0. However, now we see that this is a product which is much easier to put equal to 0, because only one of these terms will have to be equal to 0 in order to make the entire thing 0. We see that we have a sine squared of alpha divided by 2 here, and we know that the sine will always be 0 when alpha is equal to 0 or 180 degrees. However, if we think back to our problem, which was finding the surface or the volume of this trapezoid, where alpha was this angle right here and here, we see that if alpha is equal to 0, then we don't really have a surface at all, because this side would just fall down there and this side will fall down there. And therefore, alpha is equal to 0 is not the solution that we're looking for. So we can forget about this term right here. The next term is this one right here. It's 2 times the cosine of alpha plus 1, which has to be equal to 0. Let's focus in on this one. If 2 times the cosine of alpha plus 1 has to be equal to 0, then we can very trivially rewrite this such that the cosine of alpha has to be equal to minus 1 over 2. And this is one of the standard angles. The cosine of alpha is minus 1 over 2 when alpha is equal to 2 pi over 3 or 4 pi over 3. And on the unit circle, the cosine minus 1 over 2 would be here, so minus 1 over 2, and this corresponds to this angle right here, which is the 2 pi over 3, or of course the other one, this angle right here, which is the 4 pi over 3. However, looking back at our angle in our actual problem here, we wouldn't want this 4 pi over 3, because that would mean that our side would be somewhat like this. And then all the water will flow out, and that's obviously not what we want. So also this solution can be dropped, and we are left with only one solution. Alpha is equal to 2 pi over 3. And this is the angle, let's go back to the beginning, this is the angle that makes the surface of this cross-section maximal, and the maximal surface of this cross-section will correspond to the maximal volume of our 3D structure, which is what we were asked to find. For those that stuck all the way to the end, you can congratulate yourself because this is quite a long exercise. And if you did, let me know in the comments down below so I can also congratulate you. If you learned something, give this video a thumbs up. And if you want to see more, you can also subscribe. And with that, I'll see you in the next one.